Hi there, everyone. Thank you very much for joining us today for our webinar on fundamentals of RF and microwave power sensors. We thank you for your attendance and participation. If you have any feedback or other webinar topic suggestions, then please let me know by chat, or you can email me later at marketing@testforce.com. Before we get started, I'd just like to let everyone know that this webinar will be recorded and you will be receiving an email afterwards with the recording. So you can go ahead and share it with anyone you think would be interested, or you can rewatch it if you like. If you're interested in any of the other webinars we'll be hosting, or to download any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy and you'll find everything you need right there. If during the webinar you have any questions, make sure that you ask them in the Q&A section in the right side menu bar, and we will be sure to get to all those questions as we come to the end of the presentation. And now, without further ado, let's jump right in and talk about fundamentals of RF and microwave power sensors with Lawrence Wilson.
Hello and welcome to this presentation. My name is Lawrence Wilson. I'm a product manager at Rohde Schwarz, and my area of responsibility are power sensors and signal generator products, and I focus on the US and Canada markets. And in today's presentation, what we're going to talk about is the fundamentals of RF and microwave power sensors. I would like to cover basically what they do, the different measurements they make, and also how to configure them, how to select the right one for your measurements, and even talk about some of the different ways how you can integrate them into your test setups. Before I go any further though, what I would like to do is just get some terminology straight. Talk about the two key phrases that you'll hear a lot when you talk about power measurements. The first one is power sensors. Now the power sensors, and that's what I've highlighted here in the graphics, is actually what makes the measurement. It measures the power. The power meters, they're used to read the values from the sensors and display the results to the user. To get the measured results from the sensor, it has to be connected to some sort of device. Power sensors generally don't have any kind of display or control interface. They do make the measurement, but they do need another device to configure the measurement and to display the results. Now here is the agenda for today. First of all, we're going to talk about selecting the right type of sensor. Then we're going to talk about the performance, how it's defined, how you configure it, and how you can make your trade-offs to get the results that you desire. Then we'll finish up the presentation by talking about different ways how to operate the power sensor. So first thing you need to do is kind of figure out what power sensor you want to use. And to do that, you need to understand what you need to measure. And this is no different from any other piece of test equipment you're going to select. You need to figure out what you want to do. And the number one thing is really going to define the type of power sensor and how you configure it is the signal. The signal you're going to be measuring, is it a CW signal? Is it an analog or digitally modulated signal? Is it a pulse signal? Is it a radar pulse? Something like that. All these types of things, all these signals have different characteristics, and they're going to make a big influence on the type of power sensor you want to use. The next thing that you need to consider is the power measurement. What kind of measurement do you want to make? Are you just looking at average power? Or do you want to analyze some time slots within a digitally modulated signal? Do you want to look at the envelope of a pulse signal? Or do you want to do statistical analysis like CCDF, etc.? All these things are going to go together and actually determine what type of power sensor you want to use for the measurement. Now let's look at some of the measurements you can make. The most common measurement to make is a continuous average power measurement, or as it's more commonly known, just average power. And what we're doing here is we're measuring the signal's average power asynchronously within a definable time interval. And what that really means is we're using a sampling window, that's the time interval, and we're going to measure the signal within that sampling window. So the width of the window is called the aperture. So that can be defined by the user. You can define how long you want that sampling window to be, the aperture time. Now, the longer you look at a signal and the more measurements you make, the more accurate it's going to be. However, you're also going to increase measurement time. So it's that classic engineering trade-off of measurement time versus accuracy. Hopefully this graphic here will give you an idea of what is possible or how it really works. We've got a signal changing over time, and we've set an aperture to 10 milliseconds. We've made a measurement of the power in there, and that first measurement says it's minus 45.3 dBm. And straight after that, we're doing another sample, again for 10 milliseconds, this time minus 46.1. We do a third, and that is another 10 milliseconds, that's minus 45.7, and we do the final fourth sample period here, and that's minus 46.2. So with these 4 sample periods, the power sensor is going to come back and give us a result of average power of minus 45.8 dBm. So that's how it works. We define that window, we also define the number of samples we're going to take, we put that together, and the sensor gives us this result. So that is the average power measurement, and that's basically the building block that we use for many of the other measurements we're going to talk about, but it really is that number one measurement that pretty much everybody makes with a power sensor. Now, you may be asking, does modulation affect the average power measurement? And the answer is yes. If you've got a digitally modulated signal, especially one with a high crest factor, you are going to see some fluctuations in the results due to the modulation. Now, the way you can overcome this is you can set the sample window to match the modulation period. And if you can set those to be equal, you're going to get the best stability in your results. However, for many modulations, it may be a case of you don't know what that modulation period is. So in these cases, you want to use smoothing. Your sample window should be about 5 to 10x the modulation period, so you can make an estimation of the modulation period, set your sampling window to 5 to 10x that modulation period. Then you can increase the number of samples as well. And if you put those two things together, the bigger sampling window, doing more samples, you're actually going to be able to smooth out the results and negate the effects of the fluctuation in modulation quality. Now, the next measurement we're going to talk about here is the burst average measurement. The burst average mode is used to measure the average power of bursted signals. You see here in the diagram, we've got a signal coming on. We use the trigger level to start and stop the signal or the measurement. But what you see there in the middle is a dip in the signal. Now that dip can happen with modulated signals. Sometimes the power level just drops down for a brief moment, then comes back up. Now, if that is the case with the signal you're measuring, you don't want to stop the measurement. You want to measure the whole power over the whole burst. So you can set something called the dropout tolerance. And what happens here is if your signal drops below the trigger level, then comes back up before the dropout tolerance or the dropout window is expired, you're going to keep making the measurement. The measurement is going to continue. However, as you see at the end of the signal, when the signal drops below the trigger level and after the dropout window or dropout tolerance is passed, it's still below the trigger level, we're going to stop the measurement and we're going to calculate the power over from the start to the stop of the whole pulse interval. The bit in the middle is what you see when it's just a brief dip. It drops down, it comes back up within that window, so we're still going to keep measuring. So that's how the burst average measurement works. Next, we're going to look at the time slot average measurement. And what we're doing here is we're using the average power measurement, but we're doing it in a definable number of successive time slots. So if you've got modulated signals where you've got time slots within a frame structure of a signal, they're all equally spaced, they're all predictable, what you can actually do is define the measurement to look at these individual time slots. And we're going to measure the power in the individual time slots, and the sensor is going to return an array which has a whole list of elements it's going to have for each time slot. It's going to give you the power reading. And basically it's not combined over all the slots, you get the individual average power readings for that time slot and however many times you repeat that measurement. So you get the average power in the time slot. Now there is another measurement called the gated measurement. That provides you a bit more flexibility to define the measurement window. And this is really used when you have a non-defined structure or you're looking for specific characteristics, not necessarily a time slot, but it works in the same manner. You can define the start and stop of the gate, you can define its location, and the sensor is going to make the measurements and it's going to supply you with an array of results providing you the average power in these individual gates. So that's how Timeslot or gated average measurements work. Essentially the same thing, but one's just a bit more structured towards a defined frame structure. The final measurement we're going to talk about today is the trace measurement. Trace measurement is used to acquire power over time, and what we're looking at here is basically we're continuing to measure the power over a period of time. The results can change basically depending on what the power level is doing. But what the sensor is going to do is provide you with an array of data, and that data can be plotted in the classical XY coordinates where you see power on the y-axis, time on the x-axis, and as you see on the graph we can see we've got a relatively flat pulse signal coming on, dropping down, going off. So you can look at on-off time and see if your signal is performing correctly. So it gives you that classic time domain view of the world. One thing to note with this, you cannot use it indefinitely. It's not a way of capturing forever and recording data. Basically, each new measurement starts when you trigger the waveform, but the key thing to know is we make the waveform where we capture the trace defined by the sensor setup, but it's only going to last for so long because there's only so much memory on the sensor. We store it in that memory, we transfer it from the sensor to the power meter, and we can start making measurements again. So it's not indefinite, but you can capture for a relatively long period of time and understand what your signal is doing over time. So we've talked about a number of different measurements here. There are other ones that we've not talked about, but those are the key ones. Now, to add to that, there's also a range of different sensors. Rohde Schwarz provide a range of different sensors, as do other vendors out there. And they all look the same. How do you determine one versus the other? Well, if we start in the top left-hand corner here, we talk about multipath sensors, or diode sensors really. And they're the most common sensor out there, and they meet the majority of the measurement needs that you would have. They have the widest measurement range, and what I'm talking about here is lowest input power to the highest input power. And so they give you a nice wide range. They also do a lot of different measurement capabilities that we've talked about, and they give you the fastest results. Very fast measurements, good accuracy, wide range of results. Now, if you want to look at maybe pulse signals and do some detailed time analysis, you really need to be looking at a wideband sensor. And we'll talk about all these sensors in the coming slides. But wideband sensors are really good for looking at the time domain and pulse analysis side of things. Thermal sensors or thermoelectric sensors, these are the most accurate types of sensors, and they also have the widest frequency range, going up to 110 gigahertz. And you need these when you want the very best accuracy. And finally, we have something called the average sensor, and it's really a derivative of the multipath sensor, and it only does average power sense measurements, and we'll talk about each of them again, but they are sort of tuned to give you some other advantages. So let's go ahead and talk about all of these. The first sensor we're going to talk about is the multipath, the diode sensor. As I said on the last slide, this is really the most common sensor and by far the most popular out there, used in labs around the country. And the technology we have here is a diode-based sensor. You see the diodes highlighted there in the orangey colour. But the key thing here is you're using overlapping paths. You've got them paths, or in this case a 3-path diode sensor, and each path is tuned for a different frequency range, different power range. They cover all the frequencies, but they're tuned for specific power levels. And what happens here, and how we do it here at Rohde Schwarz, is we measure each path simultaneously. Now, we get the results from each path, 1, 2, and 3. Then we sum them and we weight them together based on the level of the signal. So if the level's in the sweet spot of one path, we're going to give that a heavier weighting than we will for one of the other paths. So we use some IP inside the sensor to figure it out. But the key thing is you're looking with 3 sensors to try and get the optimal result. And what they give you using this diode technologies, you get the widest measurement range. We've got the 3 paths, we can tune them for different measurement ranges, So you can go all the way from minus 70 dBm all the way up to plus 23 dBm. So there's a very big range to use. They're very fast and they have good accuracy. So that's your performance. In terms of disadvantages, there are some things you can't do, and it comes down to the video bandwidth being too narrow for some of the pulse modulated signals. So when you're doing some pulse signals, and if you want to look at things like rise time and fall time and do some time domain analysis, you really want a wideband sensor more than a multipath sensor, and we'll talk about that in the coming slides. But the key takeaway here is, if in doubt, multipath sensor is going to be your best bet because it's going to solve the majority of requirements out there. It's the best all-round sensor. But when you choose one, please make sure you're choosing one where it's got the multiple paths and they're all measured, they all overlap and they all measure simultaneously, because this means you're going to get the best results and you're not going to miss any information. Next up, we're going to talk about the average power sensors, and because multipath sensors are by far the most common out there, we're going to compare all the rest of the sensors to the multipath sensor. The average power sensor, as I said, is a derivative of the multipath. It's tuned to work down and start measuring at 8 kHz in terms of the frequency range. It's got similar performance to a multipath diode. So in this case here, it's got minus 70 dBm up to plus 23 dBm. It's just as fast and just as accurate. So it's got similar performance here, but it just works lower in frequency. It starts at 8 kHz and can go all the way up to 6 or 18 GHz. Now, what it does have in terms of limitations is there's a limitation in its measurement functionality. It can only make average power measurements. It can do on CW and modulate signals. So the time burst and the trace that we talked about are not available with an average sensor. So the question is, why do we have one? Well, this is really designed for EMC applications, where you really need to start your measurements and measure all the power that is being emitted from something from 8 kHz all the way up to the top of your range. So for people working in the EMC area, you're looking for an average power sensor and you're looking for one that starts at 8 or 9 kHz. And you just need to make average power measurements, so this is ideal for the job. Next up, we have the wideband sensor. And as I mentioned earlier, this is the one you really need to use when you want to analyze pulses. It's got a much wider video bandwidth. So what that does is it opens up more potential for measurement capabilities. It's got more capabilities. You can look at the envelope statistics. You can do pulse analysis, so rise time, fall time, pulse width, all that sort of thing. You can see in the diagrams the type of measurements you can make. They can also do time analysis and statistical analysis like CCDF. So there's a lot of capabilities here within the wideband sensor, and it all comes down to having that wider video bandwidth, which opens up more capabilities. So why not use this sensor for all your needs since it has more capabilities? Well, like everything, there is a trade-off. With a wideband sensor, you don't quite get the same measurement range as you do with a multipath sensor, so you can't measure the same low-level signals. And also, it's got a slightly higher measurement uncertainty. In power sensors, we talk about measurement uncertainty, which is really accuracy. So it's not quite as accurate as a multipath sensor. Where you do use them, as I say, it's really for analysing envelope power. You want to look and analyse those pulse signals. A wideband sensor is the one you want. And the final sensor we're going to talk about is the thermoelectric sensor, or people just call them a thermal sensor. And this sensor gives you the most accuracy. Hands down, thermal sensors give you the most accuracy. They also have the widest frequency range. They can go from DC all the way up, and we have thermal sensors going up to 110 gigahertz. So really, really wide measurement range in terms of frequency. In terms of measurement capability, it only does average power, so CW and modulated signals. So disadvantages of a thermal sensor, again, compared to that multipath sensor, it's got a smaller measurement range. It's got limited measurement functions. It can only do average power. But what it really excels in is giving you that accuracy. So that makes it ideal for calibration labs and demanding reference applications where you really need to have the very best accuracy to get a real reading, a very accurate reading of your power levels. In these cases, when accuracy is the #1 requirement, you want to look for a thermal sensor. So when you put that together, this chart here gives you a sort of summary of what's capable. The multipath sensor covers a lot of different measurement capabilities which it can do. It can't do the statistics and the time-based analysis, but it does give you fast, accurate measurements and covers a lot of different measurement techniques. Wideband sensors, it does it all in terms of measurement capabilities, but you give up a little bit in terms of accuracy and speed. Average power sensor, these are designed to cover those low frequencies required in the EMC world. So if you're doing EMC testing, you really need to look for an average power sensor. Then if you want the best accuracy, if you're in the Cal lab or really just need the best accuracy, you need to look for a thermoelectric sensor. Now let's look at the next part of our agenda, which is defining the performance. There's lots of different sensors out there. How can you determine which one to choose, which one is better than the other? And there's sort of four main characteristics you can look at. There's frequency range, measurement uncertainty, and speed. Frequency range, obviously that one's pretty straightforward. You need a power sensor that covers your frequency of interest. So if you're working with a signal at 7 gigahertz, you need a sensor that goes to 8 gigahertz or above. So that's what you need there in the frequency range. The one thing to remember, however, is power sensors are wideband devices. They measure everything from their lowest frequency to their highest frequency. They measure power that's coming in all those different areas, so they're not selective. So you do want to limit it. If you're only looking at signals up to 7 gigahertz, you don't want to be using an 18 gigahertz sensor because you're just going to get extra power, if you will, in there when you don't need it. So that's frequency range, pretty obvious, but let's go on and talk about some of the other things. The next one is measurement range. We've talked about this a little bit earlier on, and that's basically the difference between the maximum input power a sensor can measure and the minimum inputs the sensor can measure. The one thing to note though, these specifications usually apply to one type of measurement. We talked about the different measurements earlier, and as you can see on this chart, we've used a Rohde Schwarz NRP AS or ASN sensor, and it shows you the measurement range for each one of those different measurements. So as you can see, it varies based on the measurement. So that's something you have to be considerate of when you're looking for choosing your sensor. What measurements am I making? What power level do my signals need to have? So that's something you need to be conscious of. Then with any measurement range, the real challenge is the low level signals. High power signals, you can always put an attenuator on the input of the sensor and get it down into the range. But low level signals are really difficult because we've got these wideband devices, which means the noise floor is a little bit higher than you might be used to. So low level signals are always a challenge. Key takeaway here is when you look at measurement range for a sensor, do so knowing which type of measurement you're going to make, because all of the measurements offer slightly different measurement ranges, so you have to be conscious of that. The next one we need to look at is uncertainty. Now, if you open up any data sheet from any vendor out there and look at the specifications for power sensor, what you're going to find is a very detailed power specification sheet. It's very, very detailed, and they all provide an uncertainty specification. The uncertainty specification within a data sheet, which gives you, and here's the specs for our Rohde Schwarz NRP-AS again, these cover the internal factors, the factors we, the vendor, know about. So that's calibration uncertainty from our calibration process, it's the linearity, it's how the sensor is going to vary over temperature. And we're going to give you those numbers. And we're going to define it for a frequency range, where you're measuring the signal, the power level, because it's going to vary by the input power level, and by the ambient temperature. So if you're working in a really hot or really cold environment, you may see a difference in the results. So that's how we're going to define measurement uncertainty. And we can give you that number in dBs or as a percentage. Now there is an equation here which allows you to convert between the two if you're comparing sensors from two different vendors, and one's in dB, one's in percentage. There's no right or wrong way to do it. There's just different ways. But the key thing here is this does not reflect the overall measurement uncertainty. This is just the uncertainty of things inside the sensor. When you're making a measurement, you've got to think about everything outside of the sensor as well. So what does that mean? Well, you need to look at the test setup. And the influencers in the test setup are the VSWR of the sensor and of the device under test. Why is it important? Because as we know from our basics of RF, any mismatch is going to change how much power goes into the sensor. If we change the amount of power going into the sensor, we're going to change what the sensor's reading. It's going to read what goes into it, not necessarily what's coming out of the device under test if you have really bad mismatch between your VSWRs. So that's something for you to consider. Next up, you've got sensors or power sensor characteristics. There's things like zero offset, measurement noise, and where noise can impact you on your measurement is when you're measuring really low level signals. So if you're measuring low level signals, you need to think about how you're going to set the power sensor up to overcome that. And that can be things like adding additional time to your sample window, the aperture time we talked about, or running more averages, things like that, which will allow you to kind of balance out some of the noise so it doesn't have the same impact on your results. Then the final one is measurement settings, and we kind of touched on it here. You can set averaging, you can set aperture time, and if you're measuring low level signals, but also important for high level signals, you want to have it set them so you get the best accuracy or the accuracy you need, but you don't want to set it where you're getting the very best accuracy if you don't need that. You just need what's good enough for your own requirements and not setting it to give you the very best results, because if you do that, you're taking way more averages than you really need. You've got a longer aperture time than you really need, so that's going to take a long time to get results. The key is getting accurate enough results in the time it meets your requirements. Now, if you're in a production line, that could mean one thing. If you're in a lab, it could mean another. I don't know what your individual requirements are. It's a case of choosing your averaging and your aperture time and setting them to give you that trade-off between accuracy and speed. Now, how do you figure out the total measurement uncertainty for any given measurement? There's the uncertainty number we talked about, and there's all these external factors. Well, if you look in any datasheet from Rohde Schwarz or anybody else, you will find a whole bunch of questions, sort of equations in the datasheet for a power sensor. They're all in small print, they're all very well documented, and I do believe it is worthwhile going through at least once so you can understand everything that impacts a power sensor and where they are. So you can crunch through all these numbers, or you can use a measurement uncertainty calculator. We've got one which has all the specifications for our power sensors preloaded. You can download it from our website. Then you can go in there and you can set the frequency and the power level, the mismatch from your DUT. So you can put in the VSWR of your device. Then you can play with aperture time, the number of filters or number of averages you're doing, and see what impact it is having on your results. And the calculator will tell you the measurement time, and it will tell you your measurement uncertainty. So it's a very quick way of allowing you to figure out how to configure your settings for the sensor to give you the best results in the time you need them. So key mismatch is really an issue in the setup. You want to reduce that as much as you can, and if you want to reduce uncertainty, increase the number of averages or increase the aperture time. Another thing you can do to overcome the impacts of the VSWR, and I keep going on about this because this has the biggest impact on measurement uncertainty. This chart here shows you the breakdown of where the uncertainties come from. And you see the big bar on the left-hand side of the chart, that's the total uncertainty. The second bar is the contribution from mismatch. Then you have the other contributions that add to it. Now there is a feature in power sensors called gamma corrections. And this allows us to correct for basically the mismatch when we know the reflection coefficients of the sensor and the device under test we can load that information into the sensor, and it can account for that mismatch, and it's going to reduce the overall uncertainty. And you see in this example here, we've managed to bring the total uncertainty down from about 0.29 of a dB all the way down to 0.1 of a dB. So it's a big difference. Obviously, you always want to try and match the device under test and the sensor in terms of VSWR, but a big way to go at is making sure you've got the same connector types. You don't want to have to put an adapter in there in between your device under test and the sensor, because it's going to have an impact on VSWR. And as you can see, it's got the biggest impact on the uncertainty measurement. Given how big a factor reflection coefficients are in measurement uncertainty, you can improve the accuracy, especially if you've got things like cabling and attenuators, splitters in between your device under test and the sensor. In the last slide, I just told you all those things are bad because they're going to add reflections. I understand that, we understand that, but obviously there's a real need for them. You can't always connect the sensor straight to the interface of a device under test. But what you can do is, if you know the S parameters of your test setup for all those cables and antennas, attenuators, splitters, etc., if you know all of those, we can load them into this power sensor, and we can adjust for that as well. So we'll load that information into the DSP in there, and essentially what we're doing is moving the measurement plane from the input of the sensor all the way to the output of a device under test. So we're making the measurement at the output of a device under test rather than after all the fixturing. So it's another way where we can compensate for some of those external components that you just cannot get around, that you have to have something. So you can compensate for them. If you're doing this, it will also improve your measurement uncertainty. So the final piece you need to look at is speed. We've talked about this. What is speed? How fast is fast enough? Well, for everybody it's different. But the one thing you'll see when you're looking at a data sheet for a power sensor is when we talk about measurement speed, we talk about readings per second. And that's basically how fast we can read the power. The sensor can make a measurement. And this is very different from measurements per second, because reading is the time it takes to make a single power reading from a device under test. But we've talked about averaging, we've talked about sampling and smoothing and all these things. Once you add those in, you might have to make multiple different readings before you can take a measurement. And that's what we're talking about here. So we take how many readings per second is different from how many measurements per second. So you just need to be conscious of that. And the key thing is, a measurement is made up of enough readings that you need so you can average out the result to get the desired accuracy. So that's what you need to do. You need to be conscious of the time. So it's the time to deliver accurate results. It does depend on more than the speed though. So we're talking about making fast measurements, but it's also about how many measurements or how many readings you really need to use. And now let's look at this example to try and understand that more. Let's say I want to measure a signal that's minus 60 dBm, and I have a required accuracy of plus or minus 1 dB, sorry, 0.1 dB. So I want to measure very accurately a minus 60 dBm signal. So I've got two sensors. The first sensor I have has got a noise floor for my average power measurement of minus 67. So that's as low as it can measure. Now what I've done here is I've made measurements on a minus 60 dBm signal, and to get it within that accuracy of plus or minus 0.1 dB, I've got 4 different traces that you see here. The grey one is with 1 average, the black one is with 4 averages, the green one is with 16, and the red one is with 64 averages. So when I kept averaging it out, as you can see, the variation from result to result is getting smaller. And when I've done 64 averages, I've got the accuracy I want. So that's the measurement. So I had to make 64 averages to get the accuracy I want. Now I use another sensor. This sensor's got a noise floor of minus 70 dBm, and I make exactly the same measurements. And what you see here is I can actually get the accuracy I want with just 16 averages. So the key thing there is I'm averaging less. So I can get, even if I've got two sensors who have the same speed, so they can make the same amount of readings per second, with sensor 2 I need to make less readings to get my measurement results. So it's very important to consider everything, not just the speed, but also things like noise floor and the actual settings required to get the accuracy you want. And in this example, what you're realizing here is 3 dB lower noise floor enables me to get the same results 4 times faster. So even if you're not worried about choosing a sensor that's got real low noise floor, because it's you're not measuring down there, the lower the noise floor, generally the faster you're going to get your results, because there's just less noise to average out in the sensor. So there is that relationship between speed and accuracy. It's a classic engineering relationship. They're tied together. To get accurate results, you need an accurate sensor with a low noise floor that can make quick readings. That's the key. You want to make sure it can do fast readings. It's got a low noise floor. That means it has to make less readings. And if it's accurate, again, you need to do less averaging. So accuracy and low noise floor means less averaging. Being quick means it's just quicker to do things. And the combination is to really minimize the number of averages you need to do to make an individual measurement. So that's the key thing here, getting all these things together. But accuracy, speed, and noise floor all affect how accurately you can get your results. Now let's look at the different ways you can operate your sensor. As we said right at the start, the sensor makes a measurement and calculates the power, but you really need another device to be able to configure the measurement and also to be able to display the results, because ultimately we need to see the results of what we're measuring. So let's look at the different ways, and as you see in this little chart, we've got one up in that top left hand side with a traditional power meter as a display. Now that you've got sensors which you really just need a display device, you can use a laptop or a tablet if you want, and you can control the sensor from there. You can actually control power sensors from other test equipment. In this case, we're using a spectrum analyzer, but signal generators or vector network analyzers can be used as well. Then also, with sensors that are enabled with a LAN port, when you use those, you can connect to them anywhere from as long as you're on the same network. And that opens up a whole host of new applications for power sensors. And we'll talk about some of these in the next slides. So the traditional base unit or traditional power meter, why would you still use one of those? Well, this is a great way where you can manually control and make measurements for a front panel. So if you're in the lab, you're very hands-on making measurements, power meter is a great way to do this. And it also has the ability to control multiple sensors from a single instrument. So you can control and make measurements on 4 sensors simultaneously. It has a single trigger point, so you can trigger all sensors at the same time, get your results time correlated right away. If you're doing it in a remote environment, it gives you a GPIB, LAN or USB interface. So it gives you a lot of flexibility how you want to operate it, either manually from the front panel or from a remote setup. Also, a big thing, if you've got a test setup already in place and you've got an old power meter you want to replace, this is a great way of doing it because it's got code emulation. So you can put in an emulation mode so you can drop it into an existing test rack and not have to change the code, because that's where the time is, when you have to change your production code or your test scripts to account for a new piece of test equipment which is doing the same job as the old one. When you use an emulation mode, you can drop it in and you're pretty much good to go without having to change your test code, which is a key thing. So the base unit does give you a lot of capabilities. It gives you a nice display, single trigger point, manual mode for setting up measurements, and the ability to speak to it over any kind of interface, GPIB, LAN or USB. If you're just doing some maybe ad hoc measurements or you're in a bit more of a mobile environment, connecting to the sensor from a PC or tablet over the USB interface is the way to go. All sensors come with software that allows you to control it from a PC. It just drops down typical Windows interfaces and really removes the need for a base unit or a power meter. It doesn't give up any functionality. You can control the sensors all the same way, you get the same results. It's just how you're interacting with it. You're using the PC to control it. And it really does enable quick and easy setup of power measurements. I really recommend this to people who are maybe working with power sensors a bit more infrequently, where they pull it out of the closet or they pull it out of the shelf, the storage area, and they just need to make a quick measurement. You can hook it up to a laptop or a tablet device and make a measurement pretty quickly. You don't have to worry about powering the base unit and the power meter, that sort of thing. Ideal for the field or ad hoc measurements. So all sensors now today, you can do this with USB interfaces standard. What is new with sensors, and this has appeared in the last couple of years, is LAN sensors. LAN sensors have all the same capability as the USB sensors we've just talked about. Same performance, same RF capability, but they do have an Ethernet port on them. And they've got a built-in web server in there, so it allows you to access it and control it in real time by anything that's on the same network. You can be over a Wi-Fi network, you could be on your corporate network, or you could be on a private network within your lab, and you can control it. You can access it that way. If it's in an ATE system, you're controlling your spectrum analyzer and signal generator over Ethernet. You can now control your power sensor over Ethernet as well. But also opens up applications for remote monitoring. You've got that broadcast tower up on the hill. You want to monitor the power it's sending out or receiving. How do you do that? Well, before you had to put a power sensor up there and a power meter or a laptop. Now you can just put a power sensor up there. You've got Ethernet connection to it. You can sit in your home office or in your lab and monitor the results without getting out and without having to go on site. So it does open up a whole new capability there because you've got basically the internet. You can connect to the sensor from wherever you are as long as you're on the same network. So in summary, hopefully that's given you an idea of some of the ways to use the sensor, but more importantly, it's giving you an idea of how you've got to really look at your signal type and the measurements requirements when you decide the type of sensor to use. And that is really important because that's going to impact the accuracy of your results and it's going to impact your measurement time. So understanding the signal type and the measurement requirements is going to help you choose the right type of sensor. Then when you're comparing sensor performance, it requires more than just comparing banner specs. You've got to look at all the factors in there. You've got to look at accuracy, you've got to look at noise floor, and you've got to look at measurement speed, and you've got to combine them all together to make sure you can get the accuracy you want in the time you need it to be. And that is a real key thing here. So once you've got that, you can understand which sensor's better suited to your environment versus another one. Then the final piece is looking at the overall test setup. That's going to impact the accuracy of the results. We talked about mismatch, we've talked about a number of other things there. You've got to look at the whole picture because everything in there is going to impact the accuracy or uncertainty of your power measurements. Rohde Schwarz, we have a full range of power sensors, LAN sensors, USBs. I would encourage you, if you're interested in this, to come and find some more information from us. We've got a homepage. If you go to Rohde Schwarz homepage, you can select on power sensors, and in there you're going to find our uncertainty calculator, selection guides, application notes, software, all the things we've talked about today to provide that support and information. So thank you very much for your time today, and I appreciate the time you've taken to listen to this presentation. Thank you very much.
That was great. Thank you, Lawrence, for presenting today and for the very informative webinar. I'd like to say thank you to all of our attendees who made the time to sit in with us for this webinar and for your participation. As I mentioned at the beginning of the webinar, this webinar was recorded and we will send out an email with the recording in the next day. We have a new lineup of webinars coming up on our TestForce Academy, so you can visit testforce.com/academy, and we're always open to hearing your suggestions as well. So stay tuned and reach out if you'd like. We have had a few specific questions come into the Q&A section, and we'll be getting back to you by email where the presenter and your TestForce technical account manager can get back to you directly with more information. I'll also leave the chat open for the time being in case anyone else has any questions you'd like to ask or that you might have thought of. And if any questions come up later, then don't hesitate to reply to my email or send a message to marketing@testforce.com, and we'll get back to you with the answers and put you in touch with the right person. We've come to the end of the session today, but I look forward to hearing from you all and hope that you have a great day. Thanks again and take care.